Materialism was, for most of Western history, the kind of eccentric view, I think for very good reasons. If you analyze it philosophically, it falls apart very quickly.
If this is correct, what we're saying, that the universe is set up for us not only to live, but to discover the properties of the universe, then we're living in a truly extravagant universe.
Well, it's great to be with all of you. And thanks to Park City's Presbyterian. This, again, I know John's thanked everyone. This is just a beautiful church to do this. And it's funny, so when Guillermo and I were working on the original book, so we're talking from about 2000, and then it came out in 2004, we thought, once we realized it would be released in 2004, we knew there was going to be a total eclipse that was going to traverse the United States in 2024. And we said, hey, maybe we'll do a 20th year anniversary edition of this book in 2024, which is one of those things you say because you don't think that's ever going to happen, right? And here we are. And fortunately, the predictions are right. There is going to be an eclipse. So it's a sort of nice connection. And as you'll learn in a minute, eclipses actually play a key role in the argument of our book. Well, John introduced the conference actually giving you an idea of this widespread claim that's very popular, at least among science popularizers and thinkers. And it's a kind of combination of two ideas. The first one that you're familiar with if you followed Discovery Institute's work for years is this idea of materialism. Materialism, in this sense, doesn't mean, liking nice cars and things like that. Materialism is a metaphysical belief, and it's just the conviction that matter is all that matters, that matter, space, time, and energy, the physical stuff that we see around us, that's the foundation of reality, and there's nothing beyond it. And this is a widespread, very popular idea among elites and intellectuals, but it's also, if you look even just at Western history, an extreme minority position. We're at a weird moment in Western history in which it's the prevailing view, when in fact materialism was, for most of Western history, the kind of eccentric view, I think for very good reasons. If you analyze it philosophically, it falls apart very quickly. For instance, if you think you're just material and everything about you is determined by the laws of physics, it's very hard to say how you could have agency and free will or follow logical arguments and propositions that lead you to the conclusion that materialism is true, right? And so materialism almost always ends up kind of refuting itself philosophically, but it's just very, very popular, and it's often conflated with natural science itself. And that's where it really gets into trouble, because science, properly construed, is about the study, natural science at least, about the study of the physical universe, the search for the best explanations for various phenomena in nature, no holds barred. That doesn't sort of presuppose materialism or anything like that, but materialism is sort of parasitic on the success and prestige of science, and so that's part of the reason I think that it's so popular. But of course, the late Carl Sagan, who was for decades in the United States the popularizer of astronomy, had a great series in 1980, I think, called Cosmos on PBS that was more recently updated and redone. But in this series, at the beginning, is a very nice voice. He said, "The cosmos is all that is, or ever was, or ever will be." Now that's a doctrinal statement. If you are Presbyterian, that's going to sound familiar to you because it sounds like the Gloria Patri, right? And so what theists, Christians and Jews, and I assume Muslims, would attribute to the Creator, Carl Sagan attributed to the cosmos. The cosmos is all that is, or ever was, or ever will be. Now what's interesting about the claim is that in 1980, Sagan and scientists all knew this wasn't even actually true. It was known that the universe actually has an age, and so there's a finite past, and so it hasn't always existed. So already in 1980, the cosmos was actually a really bad candidate for ultimate explanation because it had a beginning. It wasn't forever. But that shows you the kind of metaphysical pressure that Sagan could say this, apparently with no embarrassment, that it was contradicting his own convictions about what was true in cosmology. So that's materialism. But then within that framework, especially when you're dealing in astronomy, there's this kind of a sub-theme of materialism, and it's called the Copernican principle. Now, the term is based, of course, on Nicholas Copernicus, who is the guy that at least in the modern era, first proposed that the Earth was a planet that orbited around the sun like the other planets as opposed to the other way around. It doesn't really, the Copernican principle doesn't really have anything to do with him, but the basic idea is the claim that science, the more we learn about science, the more we learn how unexceptional and unspecial we are, how happenstance we are. So that the idea is there's this kind of historical narrative in which the more we learn about science, the more we realize how insignificant we are, both in size and in the scheme of things, that is, metaphysically. That's the Copernican principle, all right? It was claimed to be based on science. So there's a great book by Sagan that we sort of treat as the foil in The Privileged Planet. Book's called Pale Blue Dot, and there's a famous passage in this book that we actually talk about in the documentary The Privileged Planet, and it was an episode in which Sagan had persuaded NASA engineers to turn around one of the Voyager satellites as it reached basically the orbit of Pluto. So on the outer edge of at least the inner part of the solar system. And it was designed actually to study the sort of outer solar system. He got them to pivot it and to take a picture of the Earth from something like 4 billion miles away. And when they developed the picture, what's interesting is, of course, the Earth is just this pale blue dot. But there's this little gleam of light that comes across, and it's an optical effect because of the light of the sun. And so I want you to just listen to Sagan's reflection of this, because it's the perfect distillation of the Copernican principle. He writes, because of the reflection of sunlight, he's talking about this image now, the Earth seems to be sitting in a beam of light, as if there were some special significance to this small world. But it's just an accident of geometry and optics. Our posturings, our imagined self-importance, the delusion that we have some privileged position in this universe are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. Don't you know this guy was a lot of fun at a party, right, with this stuff? I mean, here we are. Now, that's a lot of interpretation to draw out of a single picture from the Voyager satellite, is it not? That doesn't look like a kind of really, really careful empirical research you'd expect from a scientist. I mean, this is obviously just, kind of metaphysical reflections based upon an image that I don't think has any kind of metaphysical specificity at all. That's the idea of the Copernican principle, though. But what's interesting about it is that in this case, it's based upon this impression that somehow size equals significance. Bijan mentioned this at the very end of his talk, this kind of conviction that, well, if you compare, I don't know, the volume, physical volume of the Earth or a human being to just the volume of the solar system, yeah, it's quite tiny. The volume of the solar system to the galaxy, okay, yeah, it's quite tiny. The galaxy compared to the size of the visible universe, oh yeah, it's quite small. Notice no one arguing this ever says, yeah, that's true, but compared to a quark, we're huge, so we must be really important, right? Nobody ever makes that argument, but it's the same argument. It's dumb in both cases. Nothing follows. And so it turns out the Earth, the size scale, logarithmically speaking, if you did a logarithmic scale, the size scale, incidentally, of the human to Earth size scale, it's actually kind of the middle. If you think of the largest things and the smallest things that we know of. Again, it doesn't tell you anything about significance. What we want to know is, okay, based on things that would matter, that are relevant, is it true that the Earth and its inhabitants are exceptional or unexceptional? And if you frame it that way, it's an empirical question, as you saw. It's both a theoretical question, theoretical in the sense that we know the laws of physics. The periodic table of the elements is the same everywhere in the universe, and it's filled in. Aren't a bunch of chemicals and elements still waiting to be discovered? So that the same chemistry that's true here, the same constraints on what you would need for life that are true here are true everywhere else. So you can already, just from our knowledge of chemistry and physics, exclude virtually all of the known places in the universe if you're wondering about its compatibility with life, which is presumably kind of an important question, right? And that's just from our knowledge of chemistry. And now we're actually discovering, as you saw in Bijan's talk, extrasolar planets, so that we're actually getting a much better sense of what other kinds of systems look like. But even within our own system, it turns out, contrary to the expectations of the Copernican principle, you've got to get a lot of stuff to go exactly right just to build one planet compatible with life. Now, by compatible with, what I mean is that it has the features, the necessary conditions for life to exist. Now, it doesn't follow that once you get the necessary conditions, life just pops up, right? It's not as simple as, okay, we got liquid water, it's around for a long time, there's some energy source somewhere, therefore you're going to get life. No, that's not what we're talking about. We're just talking about the necessary building blocks, the kind of physical and chemical preconditions for life. That's what we're talking about. We're talking about habitability. And it turns out so you're excluding the whole question about the origin and the complexity and organization of life. That's another problem. We just want to know, what do you need to get in a planetary environment where life can exist? And virtually everything we discover and have discovered over the last several decades has moved us in the direction of realizing, gosh, it turns out you got to get a lot of stuff right. And we would venture to say there's probably a bunch of other things that we still have to discover in order to find that. So this then it's not just a kind of metaphysical question. You can actually ask, is it true empirically? That is, if we compare all the things that we know already you need to have in order to build a habitable planet, on those criteria, right? Not size, not sort of color or something like that, right? But for hosting life, is it true? And it's almost certainly not true. As Bijan mentioned, that he did a terrific job of summarizing just some of the things that you need to build a habitable planet. But let me just kind of remind you of that. So remember he told you need liquid water. Water is the perfect solvent for a particular type of chemistry that you need for life. People remember what that chemistry is? Carbon. All right, so carbon is these wonderful properties in which it's stable enough that you can build complex molecules, you can build information-bearing molecules, but not so stable that it can't undergo reactions and changes and transformations, but it needs a matrix in which for these reactions to take place, and water is the perfect solvent for it. So water is liquid over the same very narrow range of temperatures over which carbon chemistry is most reactive, right? So this is the reason that NASA doesn't waste time looking for life in places where liquid water can exist. That's a fundamental kind of realistic recognition of this. And so as he mentioned, you don't need, so to get liquid water, right, first of all, you got to have the water, but it's going to need to be on the right kind of planet, a terrestrial planet with a stable surface. So he didn't even mention it's got to be actually very much the right composition. It's got to be the right size, with the right amount of gravity, not too much, not too little. It needs to be the right distance from its host star, that Goldilocks zone called the circumstellar habitable zone. The orbit, it needs to be fairly circular, so it's not going in and out of the habitable zone, right? That needs to be around the right type of star, giving off the right kinds of sort of stable energy over long periods of time. The star almost certainly needs to be a single star, not in a binary system or any kind of sort of complicated mess. It's hard enough to get 8 or 9, depending on whether you count Pluto, planets in circular stable orbits around one star. Try that when you've got 2 stars who are messing with each other constantly, right? So you can see what's happening here is that we're just narrowing it down. Every ingredient you add that's an independent ingredient, it narrows the number of stars in which you're going to have the possibility of life from all the planets around the stars that are available, all right? He mentioned also importance of a large moon to stabilize the axial tilt of your planet like ours. Plate tectonics, which, okay, if you live in California, it might be counterintuitive to realize that plate tectonics is important for life, but you chose to live in California. So I don't know what to say, you know. We like to live right near fault lines because they tend to be mountainous and pretty. So I'm sure there's a theological point in there somewhere. But it turns out that at a macro scale, you actually want plate tectonics. You need to have the right kind of atmosphere with the right elements, as he mentioned, nitrogen and oxygen rich. And again, I emphasize, this is not us being parochial and not being imaginative enough about other conditions. This is based on very well understood properties of chemistry and energetics and physics and things like this. Bijan, I think, just very briefly mentioned the importance of certain types of planetary neighbors. Now, maybe the astrologers believe that our planetary neighbors played a role in our existence in the sense that when you were born, depending on where Jupiter was in the sky, it played some kind of role. I assume that's almost certainly not true, but it turns out they probably do play a role in our existence. If we did not have these large gas giants in the outer part of the solar system, far more of the comets in the outer part of the solar system we would encounter them directly. So you can sort of think of these planets as kind of sentinels that protect the inner part of the solar system from too many visits from comets. Comets, it's sort of nice to see them, but you really don't want to have them visit very often for various reasons, all right? So they do play a role, and I think at the moment we're only just beginning to understand what the details of that are. Then you need to be in the right galaxy, a type of galaxy that's structured in an orderly way, that has the right abundances of certain heavy elements for building rocky planets. If a galaxy is just hydrogen and helium for the most part, you're not going to get any kind of planet that you'd be interested in. And then you need to be in the right galactic location, as he mentioned. And then the final thing is that you need to be at the right moment in cosmic time. There are lots of times in the early history of the universe that would be bad for fairly obvious reasons having to do with no elements and way too hot, right, and way too irradiated. And then you can sort of theoretically project out, okay, what would happen in the distant future in the universe. And astronomers and cosmologists are used to thinking in timescales of out to like 10 to the 150 years in the future, in which it's black holes sort of dissipating. It's very depressing. And so it turns out there's a little narrow range in there called the cosmic habitable age where you would want to be if you're going to exist. All right. So is that all you need for a good design argument? This is what Guillermo and I confronted when we first started working on this book. And so here's the problem. Is that unlike the sort of regular fine-tuning argument in which you're talking about one universe, when you're talking about what you need to build a habitable planet, you have to take account of the fact that there are a lot of stars and a lot of potential planets in the actual universe. And so just showing that, well, you kind of got to get a lot of stuff right, by itself doesn't answer this kind of fundamental question. Okay, is that the result of an intentional design? Or is that the result of a chance, so that the universe is like this cosmic lottery? And it's unlikely that any particular system is going to produce a habitable planet. But if the universe is big enough and has enough opportunities to flip enough coins, it's eventually going to get the 20 heads in a row or the 30 heads, whatever is required, right? That's the sort of dilemma. And so philosophers actually call this a dilemma of what's called a selection effect. And so the selection effect would be, wow, everything seems to be well-oriented and designed for us here. But it turns out there's lots of other places that we could have existed, and none of those other places are consistent with our existence. So we have to find ourselves in a place compatible with our existence, right? And now that could be a design argument if it was the only place, right? But we know there's lots of other places. Let me take it out of the human context. So imagine you don't know anything about dandelions. So you've never seen them before, you don't know how they propagate or anything like that, and you're in West Texas somewhere where you've never been, and it's in late May, it's really hot, and you're in one of those giant parking lots in one of those malls that are now unfashionable, but parking lots exist forever, right? And so there's a little crack in the parking lot, and right in the middle of this one crack in this massive multi-acre parking lot, there's a little yellow flower. Right? Now, what are the chances that that little yellow flower would just grow right there in that one crack when there's no place else, as far as the eye could see, that it could grow? Well, Okay, actually pretty darn good if you've seen how dandelions work, right? They spray all those little things all over the place, the wind takes them, and if there were 1,000,000 dandelions going white and littering the place, it's very likely one of those seeds is going to land in that crack. All right, so do you see that the point is that if you didn't know the background details, you might falsely infer design, when what you should really infer is, well, no, chance is totally capable of doing that, in the sense that if you have enough tries and you scatter enough of these seeds, one of them's bound to land in the crack. So the question is that what we're seeing? Well, we're that dandelion growing in the crack. We're the life in the one place compatible with our existence. We shouldn't be surprised we find ourselves here, but it might just be that there are, enough stars and systems in the universe that one of these things will happen by chance. Right? Does that make sense? And so it's sort of like this. I'll use another example. Imagine, you know how coins work. So let's assume that knowledge, right? The regular quarter. And I say, okay, I'm going to flip this coin 10 times in a row. All right? And I'm going to try to get 10 heads in a row. And so I say, no, let's make that 20 heads in a row. And so you all see us do it, right? You see me do it. And I start flipping and we count them. 1, 2, 3, 4, 5, 6, 7, head. Now at some point, right, you're going to get suspicious if it keeps being heads, right? You're going to think, wow, he has a magnetic thumb, or it's a two-headed coin or something, right? In other words, what's going to happen is you're going to say the opportunities for chance are very slim here, because every time he flips it, he's getting ahead. And so what's much more likely is that he's rigged this in some way than that he is by chance getting 10, 20 heads in a row. Now change the scenario. Let's say I'm going to flip this and I'm going to get 20 heads in a row, and nobody's leaving until we get 20 heads in a row. And you hear the doors lock. They bring in water and nothing. And so I start flipping these really, really fast. Sometimes it's 4, sometimes it's 7, sometimes it's 10, right? Now, eventually, most of you die, unfortunately, but a few of you grow old. The young here grow old, and they eat the other ones that died right before them. So I'm sorry, this is the story. Okay, and so, but you managed to survive for several years, and I eventually get 20 heads in a row. Now, at that point, you're going to say that was a rigged coin? No, you're going to have killed me long before that. But, you get the point, right? That chance had a lot of room to operate, so there's nothing special about the fact that I eventually got 20 heads in a row. You see the point? And so what we don't want to do is make glib sort of design arguments based upon things like this, unless we've got sort of something else to show for it. Because that's the sort of difficulty. Even if you need to, say, 20 elements to go right, and each just has a 10% chance of occurring, you've got a very large universe. You've got something like 10 to the 22 stars in the observable universe, and presumably lots of those have planets around them. And so, maybe you could just given the laws of physics in a very large universe and enough time, you're going to get a few habitable planets by chance. Now, there would actually still be a fine-tuning argument behind this, the level of the universal constants and things like that, right? But I'm just talking about within the universe. So there's the question now that I've set this up so that you say, oh, yeah, this is a problem. Is there something else we could tell you that would tip the scales, would say, yeah, I think that this sounds like a conspiracy rather than mere coincidence? We think there is, and that's what we argue in The Privileged Planet. It's this. Habitability, the conditions that allow for the existence of habitable planets, correlate with measurability or discoverability, those properties that allow you to discover the universe around you. Or to put it sort of more in the vernacular, the same narrow circumstances that allow us to exist also provide us with the best overall setting for making scientific discoveries. Or again, the very conditions that make Earth hospitable to intelligent life, that allow a planet to be compatible with scientists, are the best places overall for doing science, that make it well-suited to viewing and analyzing the universe as a whole. That's unexpected, and that's the additional story we have to tell.
We got 2 minutes. Oh, that clock.
No.
Okay, that clock. All right. I won't panic. Okay. Okay, thanks. All right, thanks, Jay. I hope you realize how surprising that is to find yourself in that kind of universe. Uh, so to illustrate that, consider the following picture. You're confined to this little cell room where you have a cot, a little sink, maybe a toilet, and then there's a door with a slot where somebody can feed a tray of food for you. So that's your entire existence. And maybe it's a little window with bars on it to let some light in, but you can't really see anything outside. That's your entire existence. A room without a view. You're born into it, you die there. Really, if you think that we're the result of chance and self-selection processes and the Darwinian struggle for survival, then this is really all you should expect of life. Just the bare minimum to live, the bare requirements for life, nothing more. If this is correct, what we're saying, that the universe is set up for us not only to live, but to discover the properties of the universe, then we're living in a truly extravagant universe. Here's a room with a slightly better view, but still not very good. But here's really an extravagant home, right? A room with a view, something like this. Not only that, ours is even far better than this, right? We have a view of the heavens. Anybody who stepped out at night, say here in Texas outside of Dallas area with the bright city lights, has looked at the night sky, been awed by all the stars you can see at night. Have you ever asked yourself the question, why this? You know, why am I being granted this view? I don't need to see the stars to exist. I could live my entire life without seeing all this, or rainbows, or solar eclipses, or beautiful sunsets. Why all this? So really, we live in an extraordinarily extravagant universe. And not only that, but there's a specific relationship between the conditions for life, as Jay mentioned, and the conditions needed for doing science. Those two overlap. And so Bijan helpfully went over all these requirements for making a habitable planet. And these are different cases that we present in the Privileged Planet, all these bullet points, each one treated in a separate chapter, and we make what's called a cumulative case argument, where we build a case based on one example after another after another. If you just have one instance of this, one example of this, what we're calling the correlation, this relation between the conditions for life and the conditions for doing science, just had one instance of that, you might say, okay, maybe that's just due to chance, maybe just dumb luck. But if you see it again and again and again in different areas, then you start seeing a pattern. Hey, maybe there's a setup here. There's something really to this. It's not just chance. And so I'll talk about perfect solar eclipses in detail in a few minutes. But let me just say a few words about some of these others. Layering processes. The Earth has millions upon millions of natural data recorders that are constantly recording the state of the environment, the temperature, the composition of the atmosphere in the form of natural processes like the ice deposits in the Antarctica and Greenland, or lake and sediment deposits, or biological growth layers like in corals, mollusks, tree rings. All these are constantly recording the state of the environment. And today, in a field called paleoclimatology, scientists can reconstruct aspects of the Earth's past in deep time, including the composition of the atmosphere, temperature, and things like that. Not only that, they can figure out what the orbit of the moon was early in the history of the Earth. They can figure out how far the moon was, how long the length of the day was. Today we know we measure how fast the moon is moving away from us, and we can extrapolate a little bit, but with these archives, these natural archives in the Earth, we can figure out what it actually was in the past. Just amazing. No other planet in the solar system records its state and preserves those archives to the extent that the Earth does. And then they could be recovered. Not only are those archives stored, but they are stored in a way that then they're preserved and we recover those archives. Plate tectonics, Bijan talked about that, the importance of that for recycling minerals, in particular for the carbon cycle. And plate tectonics is important also for helping generate Earth's magnetic field. It's very important for life, but it's also important for discovery. We can map the interior of the Earth because of the earthquakes that they produce. And if somebody's interested, they can talk to me and Jay later about, what about earthquakes? Aren't those a bad thing? Well, yes, but they also are a mark of a planet that's habitable, because you need active geology to have a habitable planet. The transparency of the atmosphere. We live on a planet where not only light from the sun can filter through the atmosphere to allow life to exist, as, for example, through photosynthesis, but it's transparent. It's not just translucent, right? For life, the requirements of life, we need a merely translucent atmosphere, but our atmosphere is more than that. It's more than you need for life. It's transparent, so we can see the stars, and we can see the distant galaxies with remarkable clarity. What kind of atmosphere do you need? Is transparent. It's a kind of atmosphere that's carbon poor, so low abundance of carbon, high abundance of oxygen and nitrogen. And those oxygen and nitrogen, those are the constituents of an atmosphere you need for complex life. And you also need that kind of atmosphere for high technology. But I'm not going to take Brian Miller's thunder away from him. He's going to talk about that. What's the relationship between the composition of the atmosphere and high technology? He's also going to talk about what plate tectonics has to do with high technology. So I'll leave those two hanging. I don't want to answer those. I'll leave them for Brian Miller. So one more example of this. Planetary neighbors. Bijan discussed how the giant planets are important for life on Earth. And we have a very rich solar system, a solar system with 8 planets. And such a rich solar system is not that common. We know of only one other planetary system outside of ours with 8 planets. But that provides a rich planetary playpen for people like Kepler, who developed those 3 laws of planetary motion, especially the third one. That's the tough one, p squared proportional to a cubed. You need a lot of data points to be certain of that particular functional form. And our solar system provided the nice planetary playpen for him to make that empirical discovery that Newton then used to derive his universal law of gravitation. And then Einstein tested that general theory of relativity using another aspect of our solar system, which I'll get to if I have time. So the particular circumstances or the particular solar system that we live in is very important in the development of science. Okay, it's not just, Newton and Kepler and Einstein didn't just develop their scientific theories in a vacuum in a dark room without having a window to look outside. They very much were influenced by what they saw in the solar system, and that led to the discovery of these important laws. So let me just spend a few minutes discussing solar eclipses, especially since there's one coming up on April 8th. And for those of you who live in Dallas, you don't have to go anywhere, because the eclipse path is going to go right over this city, the most populous city within the path of this eclipse coming up in April. So I went to see my first total solar eclipse in 1995 in India. I timed my trip, which was a research trip with some colleagues there, to coincide with this eclipse on October 24th, 1995. And I joined an eclipse expedition in northern India, and we did some experiments. But no matter how accurately an astronomer can predict the circumstances of an eclipse, and they can do it pretty accurately, they can calculate the circumstances of an eclipse anywhere on Earth within 1 second of time, centuries in advance. They really understand the mechanics of it. Yet, there's something about eclipses that's a mystery. It's mysterious, even though we understand the mechanics. Just to remind you, how do you get a solar eclipse? You have the moon passing between the Earth and the sun, casting a shadow on the Earth. And that shadow races it across the surface of the Earth. The dark part, the umbra, is about 100 kilometers wide on average. And if you're within that part of the shadow, you see the sun totally blotted out by the moon. And in fact, it gets somewhat dark. Some of the bright stars come out during the day. You can see bright planets. You see the sun's corona, its faint outer atmosphere during the eclipse. And I've been, when I was in India and I was at that eclipse expedition, and I saw all the people around the eclipse compound where the scientists were. Everybody was equally in awe. Both the scientists and the local lay people who were observing it were equally in awe of this event. Even though the scientists could understand the mechanics of the eclipse, that didn't remove the wonder and awe of seeing the eclipse. But here's the mystery. People have noted this for a long time. If you've ever noticed the sunset and maybe the full moon rising almost the same time, you notice something interesting about them, about the sun and the moon, almost exactly the same size in the sky. Right? Have you ever wondered about that? Why are they the same size? Do they have to be the same size? I mean, why? It's about half a degree. They both obtend the same size. And for that reason, the moon just perfectly covers the bright disk of the sun during a solar eclipse, allowing us to view the entirety of the sun's atmosphere during the eclipse. And this is actually quite unusual. Here's a plot of, let me explain it first, angular size ratio for different moons, with planets with moons in the solar system, starting with the Earth in order of distance from the sun from top to bottom. And that vertical line, the vertical dotted line, is 1.0, meaning the moon will appear the same size as the sun as seen from the surface of that planet. Okay, and so I have these little dashes throughout the graph because I took into account the eccentricity of the orbit of the moon and also the planet. So that means you'll see a range of angular sizes. And so you'll see that the Earth's moon crosses that dotted line right down the middle, basically restating what I already said in a graphical form, namely that they subtend the same angle on the sky. There's another one, only one other, that crosses that middle line. That's one of the small potato-shaped moons of Saturn. That's on what's called Shepherd moon. That's on the edge of the ring system of Saturn. And because it whips around Saturn so quickly, eclipses produced by it last less than a second. That's the thing about the giant planets. They're so massive compared to the Earth that the moons around it move around those planets fast at this given separation, whereas Earth is much less massive, and so our moon moves around the Earth pretty slowly. It takes 30 days to orbit around the Earth. And so we have nice long eclipses that last typically minutes, and so we can fully enjoy them. So it's interesting that the most habitable place in the solar system is also the best place to view solar eclipses from. So is that a coincidence? Maybe we're just lucky. So I asked that question in a paper I published in a journal called Astronomy and Geophysics in 1997 called Wonderful Eclipses. And I said that, no, there's a connection between life on Earth and our ability to observe what I call perfect solar eclipses. And very briefly, put together a few of the things you've already heard. Where does the Earth have to be for there to be life? In the circumstellar habitable zone. Also within this photosynthetic habitable zone. And there's a third one, the UV light habitable zone. Those three have to overlap. And so that really restricts the kind of star that you need to orbit and the distance from the star. Turn the problem around and ask, oh, wait a minute, what would the sun look like from the circumstellar habitable zone? So the requirement that you have to be within the circumstellar habitable zone means that you're going to see your sun subtend a certain angle in the sky because it's going to fix your distance. Okay, so there's the first part. There's the first half of solar eclipses. What about the other part, the moon? Well, a large moon, relatively nearby moon, stabilizes the Earth's tilt of its rotation axis. It also helps in other ways, like with the tides, mixing nutrients from the continents to the oceans, also with the circulation of the Earth's oceans. Some of the energy from the lunar tides dissipated in the deep ocean helps to drive the ocean currents that is important for climate. So you have this large stabilizing moon that increases the habitability of the Earth, right? And so the presence of this moon, large moon, close enough to the Earth to have its life-enhancing effects, means that you're more likely to have total eclipses. In fact, the moon is almost too big. If it were just about 80 kilometers larger in diameter, it would have destabilized the Earth's rotation by now, the rotation axis. So it's a very, very close match as to how big it could be. We're right at that limit And so the requirements for life on Earth at the same time make it much more likely that you'll enjoy total eclipses of the sun. So there's this deep connection between life on Earth and our ability to observe solar eclipses. So that's the question that's been, people have been asking, scientists have been asking for centuries, and I think we finally have an answer to it. And that's not the end of the story. Not only are eclipses beautiful to observe, but they lead to scientific discoveries. And I'll just mention one here for the sake of time. I mentioned Einstein earlier. There's a certain aspect of the solar system that helped him with one of his theories, general relativity. He provided a test for general relativity when he published that theory in 1915. He said, look, go out and observe a solar eclipse, take pictures of it, and measure the positions of the stars around it during the eclipse. And my theory predicts that the positions of the stars will be shifted by a certain amount because, in my theory, the mass of the sun will bend the space around it and cause the light to have a different path than it otherwise would have. And that was confirmed in the 1919 solar eclipse, observed by Arthur Eddington, a British astronomer. And so that confirmed general relativity. Probably the most important theory in physics today. And solar eclipses had a very important part to do with that. So I'll end here, and Jay will close us.
So we've literally just sort of touched on this, but there's only one example. So if you're not persuaded, Guillermo mentioned this is a cumulative case argument, but I want at least to have you see how this works as a design argument. The question is sort of, so what? Well, design arguments usually combine two things. They combine an improbability or a complexity or rarity, right? That sort of gives you the contrast medium, and then some kind of important pattern or a telling pattern. And everyone recognizes why you put telescopes on the tops of mountains, for instance, right? Because you put observers in the best places for observing. So if we discover that's true about the universe, that the very rare places in which scientists can exist are also the best places overall for doing science, we have two hypotheses. Which one's more likely? That this is entirely the result of chance, or that this is the result of design? That's the question. And we think the more of this that you see, the more clear at least a modest conclusion becomes. The universe is fine-tuned so that environments habitable to observers will provide the best overall conditions for observation and discovery, or simply put, that the universe is designed for discovery. Thank you very much.